back to you.
Okay. Oops. Okay, next thing we're going to look at is a very important topic, and this is the topic of global settings. Okay, global settings apply to the whole batch. Okay, first of all, we've seen it as a component of method editor. They're very critical to proper quantitation. They are method-related parameters, and they apply to the whole batch, to all samples as well as all compounds that are in that batch. And this is the way we get to specify or to modify those methods to do specific applications that are involved in there. So I go into Method Edit, and on the left side I have Global Setup. Okay, this window is divided up into several little different sections, and we'll cover each of these individual items in greater depth as we go along. We have the excuse me. We have the multiplier. We'll define the multiplier and so forth. And what do we want to apply that multiplier to? Internal standard, matrix spikes, surrogates, targets. We have our choices. By default, it's applied to the target, but not to the internal standards. And obviously here also applied to the matrix spike and surrogates. We also have some bracketing type for special type of applications, how to handle a calibration curve. We also have correlation window. This is important in that target compound analysis. This is how close those peaks from the quant and qualifier ions have to be to each other, the apex of those peaks. Then I have a feature called dynamic background subtraction, ignore peaks not found. I have a library method, which is part of our unified method concept, where we have everything can be in one method, everything from acquisition to qual to quant to library method to the quant database and so forth. Then I have these non-reference and reference windows. Okay, these features here, the reference window, we're going to cover that in much greater depth because this is a very useful concept for identifying closely eluting compounds. In addition to that, I can set up a reference library. We'll talk about that. I have a relative internal standard and a standard addition. First of all, let's look at the global settings, the calculated and final concentrations. In our default layout at the batch table, you have these two columns, calculated concentration and final concentration. Typically, these are the same values. But in cases where we've used the multiplier, by definition, the final concentration is the calculated concentration. The concentration as that point, as that response was taken from the calibration curve, and then times the multiplier will give us that final concentration. Okay. Then I also have other parameters in the multiplier. The multiplier is defined as the dilution factor times the sample amount multiplier, where the sample amount multiplier is the total amount divided by the amount. Now, all three of these columns are available in the sample section of the batch table, and they're either set to 1 by default or explicitly 1, as in the case of the dilution, or implicitly for the amount and total amount. Now, when we come back to total amount over amount, say your procedure says to weigh out 5 grams of dirt. You and I both know that it's hard to weigh out 5.00 grams of dirt. And in this particular analytical method, I need to know the absolute amount of my compounds in this dirt sample. So in order to accommodate that, I would implement a multiplier into the system. That multiplier then would change or be multiplied by the calculated concentration to give me the final concentration. Okay, to get those settings, those parameters, dilution amount, total amount, and the multiplier columns up, Okay, I right-click in my batch table, select my samples or select columns from my sample, and basically I would add those 3 columns and they would appear then in the batch table. And I can change those. Those are editable fields in the system. They are also imported from a work list and or a sequence. In addition to that, I also have another field that's available for my compound method. That is also a multiplier. If I bring that over, this multiplier tells me what has been applied to that compound based on these 3 factors that are editable in the sample columns. When this multiplier, as applied or illustrated from the compound method, is not an editable field. It represents the product of these 3 put into here. So this, in the compound method, that tells me what the multiplier was for this particular compound. Okay, the next setting that I have in my global settings is the bracketing type. By default, this is set to none. So in a situation where I'm running several sets of calibrators, cal samples A, B, and C. I run my 5 cals, beginning of the run. I run a bunch of samples. I run some more cals, some more samples, cals, samples. What is happening here when bracketing is set to none is I'm taking the average of these 3 calibration sets, and then I'm applying an average calibration curve to these to all 3 of these sample sets. Well, this is good, and it's typically used to average things out. In certain applications, we may wind up not having standards that are stable over a long period of time. Okay, I'm running a very large sample sets here. So what I may need to do is run these and then quantitate based on a cal curve. So what winds up happening here, for example, my calibrators aren't stable. I have acid-base chemistry going on, ketoenol tautomerism, whatever the case may be there, and they're not stable. So what I do is if I set my bracketing type to overlap in the global settings, what the system will do is it will take cal set A, it will take cal set B and average these 2 curves and then quantitate with sample set 1. Likewise, as we continue on, it replaces that cal curve with cal set B, averages in cal set C, and then does the quantitation for this sample set 2. This, in turn, then takes care of or accommodates the instability that's in my calibrators due to some other chemistry that may be going on in there. I also have a third type of bracketing type that was recently introduced, and this is called the sample group. What the sample group is used for is for stream select. For those of you that aren't aware of stream select in LC, this is where we actually can run 2 columns simultaneously, concurrently, and basically what winds up happening there is, you run your sample on column 1. It may have a retention time set up as 1, and then you run it on column 2, and there might be a slight variation on this. This whole stream select concept allows higher throughput of our samples. What winds up happening is these retention times have varied a little between columns, and there's no way we're going to be able to change that or get that to come in. So what we could do is in our batch table or in our work list or batch table, we bring up the sample group, and this one was run on column 1, column 2, column 1, column 2. Essentially what the system will do then, if the global setting is set to bracketing type sample group, it will take all the column 1s and take those and develop a calibration curve based on those column 1s. And likewise, the same thing would occur with column 2. And this is accommodating then for that slight shift in retention times or variations in instrument response that we may be seeing. Next window that we have is this correlation window. This has to do with our targeted compound analysis. If a given qualifier is part of the compound that the target ion, the compound of interest for me, is related to that target ion, when I do an extracted ion chromatogram, and this is what Quant's doing, for the qualifiers, okay, and the quant ion, these should be essentially overlaid. In this example, what I'm seeing here is that this 113.4 qualifier ion in green is not co-eluting. So this is probably due to a matrix effect, and it may be influencing our qualifier ion ratios for this particular compound. Therefore, we have an outlier, and we need to investigate it. We have the ability to set this up. The default time is 0.5 minutes, which is a rather large window. Typically, in order to get good targeted analysis, to increase our confidence that we are indeed looking at the compound of interest and quanting that compound, typically what I would want to do here is set this to be 0.01 to 0.05 minutes. And this depends upon a lot on your chromatography. Anywhere from 0.6 seconds, the apex of these integrated peaks has to be within 0.6 seconds of each other. And then we could go up to 3 seconds is typically a tolerable range. And again, it depends upon your chromatography here, what's happening in the chromatography. But if we are doing good targeted compound analysis, and if we have clean samples, essentially the profiles of the target ion and all the qualifiers, retention time should match up identically, as well as the peak shapes, generally speaking. If they don't, there's high probability that we may have a matrix interference, which may be interfering with the target ion that we're quanting on, or it could be one of the qualifiers as shown in this example. Another global settings that we have is called dynamic background extraction. This is toggled on or off. And essentially all that this algorithm is doing is removing noise or background ions from our TIC, our total ion chromatogram, as seen in the sample information window. So really, here's before dynamic background subtraction. You notice we have a very high baseline here. And then after dynamic background subtraction, you see that that baseline is gone. All right, what value is this? Well, essentially all it is the TIC in the sample information chromatogram there. What the algorithm is doing here is looking for ions, excuse me, that have no specific peak shape associated with those when we do the extracted ion chromatogram. Background noise, for example, column bleed from a GC column, the 217, 281 ions, 207, 281 ions that we typically see as background from our GC columns, those would be subtracted out, therefore lowering that background at these higher oven temperatures as we're doing an oven gradient. Okay, next window. Now this is another important global setting that we have. And these two are combined. They're separated here, but they're two combined. They're the same concept involved in here. Okay, what we're doing here is we're extracting out the baseline. We have peaks that may be co-eluting with the same target ions. This is the extracted ion chromatogram, right? We extracted that out. Have some other peaks that are related to this. The non-reference window applies to all the target compounds, i.e. all the compounds that are not labeled or flagged as time reference. The way I got to this window here was in the method editor. I went to the internal standards setup, and this is where I would set up my internal standards, fluoro, chloro, fluorobenzene as they're related, surrogates and so forth. They're labeled internal standards here, concentrations filled in. Now, if I make that compound a time reference compound, the reference window refers to any compounds that are time reference compounds. What happens here is if a compound is a time reference compound, And it has to be an internal standard. It has to be present in every sample. So the only thing you can label in the method editor is the time reference, is an internal standard as a time reference compound. What happens here is the system goes through and it looks for the time reference compound. It extracts it out as it normally does. Say this peak normally comes out at 10 minutes. Right now it's coming out at 0.6 minutes. What the system will do is an on-the-fly calculation adjusting all compounds related to that internal standard. It will adjust that, as in my example here, 0.6 minutes. It will add a plus delta RT, move this window over. Generally speaking, we want to find the reference compound first. And we have these little red hash marks, which you can visualize, and we'll show you in a minute how to do that. I generally make my reference window wider than my non-reference window. I want to find that time reference compound first, and then make the adjustments and a tighter window for using this. This is a good way to prevent or minimize the misidentification of peaks, especially in certain situations where we have lots of co-eluding things, lots of matrix interferences that may be coming into play. So these are generally very, very important for minimizing misidentification of peaks. All right, in order to get this to display, I showed in the previous slide, we have these hash marks or these marks. If I right-click in my compound information window, go to Properties, I can show the reference retention time. In this one, I check this box, and I left it dark blue, and I said my style, just a vertical blue line. This is the reference retention time. This is the expected retention time that this peak is supposed to come out at. And you can see in this example, it's pretty close to the 2.02 minutes there as designated. Then I can also come into my Properties window and display the recognition window. Now this is a little bit confusing because the recognition windows in this Properties is the correlation window, is the reference time, is the reference and non-reference windows in my method editor. And I could display those. In this example, turn the check on, I made them red. Here are the red hash marks. In order for this peak to be identified, the apex of the peak, after it's integrated, has to fall in these red hash marks. This is how I get rid of those isobaric compounds that may be due to matrix impurities, or maybe a compound with similar transitions or quant ions that we're looking at. The apex of that peak has to fall in between these two lines in order for that peak to be identified. Then in global settings, I also have the ability now to set up a reference library. Well, what is a reference library? A reference library is typically used with scan type data. It can be used with transitions where with MS type data, where I have a couple of transitions that I may be looking at. What this does is it gives me a reference spectrum that I can visualize or compare my spectrum to in the compound information window. What I could do is create a reference library from a sample. In other words, what I would pick would probably be a mid to high range calibrator, and I could obtain the reference spectra from that sample. Or if I have a small user-generated library, I would typically look at or create that. Once I create that library, it creates the library and gives you a reference to where that library was. Then what winds up happening is when I come back into my compound information window, what I have now is my target scan, the reference spectrum that I can compare peak by peak, mass by mass, and see how close. You can see here I might have a little impurity or a little peak splitting going on, but generally speaking, this is good. What I've done here now is I've taken my target scan from each of my samples and/or calibrators, and I've done a library search on that, comparing it to that reference spectrum. I could bring up another column in my batch table called the library match score, which tells me how close that reference spectrum or the target spectrum came to the reference spectrum, which I know is generally pure. And then in the compound information properties, tab 2, I have various ways to display this. I could display the reference spectrum, as I did here. The library source, here's the library source, which in this case was one of the calibrators. You can see it's Cal L09 in this example. Reference pattern spectrum, this would be related to, again, the pattern, typical with TOF and QTOF type data, high resolution data, where I set up the isotopic grouping. I can override, I can show the match scores in here, so I don't have to bring up the column. I could show it right here in the compound information. This is then increasing my confidence as I look at this data that I am indeed targeting the compound that I want to be targeting and not some impurity due to the matrix effects. In addition to that, I can also show these mass indicators. What is my target ion and what are my qualifier ions? Okay, last global settings, as we're moving along here, is relative internal standard. Who remembers, we had a question last week on how to semi-quant. We answered that question. How many people, why don't we send a chat message to Lindsay right now? How many people remember how to semi-quant? What did I have to do? I had to go into the method editor and do something in order to semi-quant. Well, I also have another method or procedure for semi-quantitation, and that is called the relative internal standard. Relative internal standard will quant all my compounds based on the response factors of the internal standard. This is obviously, semi-quant is particularly useful if I don't have authentic samples, clean samples of my target compounds that I could weigh out and quantitate on or calculate the response factors. So all that this is doing here is taking the response factor of the internal standard and applying that to all the concentrations, all the compounds. It's using the same response factors. Well, say in an instant, my internal standard happens to be an alkane, and I know the response factor for an alkane versus a halogenated compound may not be the same. Well, I have this internal standard relative multiplier, which I can add to my method table, my method editor table, and I could put in a different value for all the compounds, target compounds, that I'm semi-quanting relative to the internal standard. Last question here we had earlier today, method of standard addition. Well, what is the method of standard addition? The method of standard addition is where I take a sample and I extract out my sample. I then divide it into 3 aliquots. To the first aliquot, I do nothing. That's my standard. To the second aliquot, I'll add a known amount of my target compounds, 1 microgram, whatever it happens to be. To my next aliquot, I will add a different concentration, 2 microliters, or whatever it happens to be, to that aliquot. Then what I will do is set up my samples to run, and it has to be run in this order in order for it to do a method of standard additions correctly. I run my sample. Then I run spike 1, which is at a known concentration, level L1 in this example. Then I run spike 2. What the system will then do is calculate a 2-point calibration curve based on the known concentrations in these 2, extrapolate that down to the 0 concentration, and then report the concentrations of this sample. Well, method of standard addition is one of the most accurate methods of quantitation. It will take into account any matrix effects that we are seeing. And this becomes very, very important there as well. But the take-home message here is if I am going to use standard addition, what I want to do is make sure I run sample, cal1, cal2. Sample, cal1, cal2. Last but not least, training resources that are available. Agilent has classroom training that's available to us. We have customized on-site training, and then we have online. This webinar will be offered as an online source of training, and it will also be available. We have other training courses at Agilent University. We also, to get to Agilent University, just go out to the Agilent website and essentially go on the home page, go to and then view all training courses here. There's a whole bunch of good courses that are out there for the MassHunter environment. And in fact, for attending this course right now, you have a free pass here for 100 Agilent University credits that are available to us. Okay, and this expires October of 2017. Just register at Agilent University, and essentially you can use this credit and review any courses. And it doesn't have to be MassHunter. There are a lot of open lab ones there as well. In addition to that, we have some other ways for you to keep up on MassHunter quantitative analysis. There's the Agilent website and so forth. Lindsay's now put up a poll, if you'd be so kind as to fill in 4 questions, very simple questions there. Let us know what you thought of today's seminar and so forth there. Any things that any features that you would like to see in future seminars also, and just submit those there. Right now, do we have any additional questions from today's work?
Oh, we definitely do. But Steve, you took the words right out of my mouth. That poll is now open on the bottom right-hand corner of the console. So for those of you who have your screen maximized, you might need to minimize that in order to see the poll. But we do ask that you take that 30 seconds to fill out those questions. It really does help us improve webinars for future. Remember, this is an ongoing series, so we will incorporate some of these comments and suggestions that you make into future events. Okay, we will go to the final question and answer session. For those of you who haven't figured it out yet, you can drop those questions into the Q&A box on our WebEx console, or you can, of course, press *1, and Alan will open your line. So let's go to the first question. I'm not sure if you can explain this or if you'll need to live demo this, but can you please expand on where to save a method to an independent file for later retrieval, other than just going back to previous batches every time?
Howard.
Well, yeah, sure.
You get the ball back and let's show them.
Yeah, I'll do that for you. Sure.
That's the easiest way to do this one.
All right, yeah, so like I mentioned, there's 2, are we, yep, we're back there, I think. So yeah, once we go into the method and edit, we'll have a few different options once you get everything set up the way you want in your method. We can, now there we go. So now we can do a save as in the method. All right, and once we do that, we get the option down here. We can either save into the standard Agilent.m folder format. We call it a method file, but in reality, as most of you know, if you've gone out into the file system, just like the data, what we call a data file, it's really a data directory or folder. You know, so we can save it as a standard Agilent method if we want to be able to bring it back into another batch. And we can also, one thing I really like, especially for portability, especially here in the call center, can be helpful. Customers you can save your method out as one of these .xml files, and then I'll show you, and it's can be brought in just like the .m type method, but it's one nice, concise file that has all of the quantitation method settings in it. And if you have any issues, sometimes we might ask, well, can you send us your method? And that would be a nice, easy way to do it. It can also be helpful just transferring from computer to computer in a lab if you want. And then I think I mentioned before, then once you have that, then you can always open from an existing file, and you'll notice that our choices then are both, we can search for either the .m or the .quantmethod.xml, and there's the one I just did. Open that, and then if I do an exit, apply to batch and analyze, then that method has been applied to this batch. And now if I save the batch, it'll be saved, and I think we discussed this a little last week, but all those things are already saved in the batch. And I guess as you noted in your question, the other way to go get them, you can open a method from a batch as well, because that information is within the batch file or folder system. But those are two options for saving the method out to an external file or folder that can then be makes it a little more easily transported.
Okay, thank you. And also, just on that note about last week's event, we'll be sending a copy of today's recording, PDF of today's presentation, as well as the link from last week's event, so you can easily reference that. I know we keep referring to that, and some of you may not have attended that event last week, so that'll be available for you as well. Okay, the next question. Why is dynamic background subtraction generally not recommended?
Okay, I could take that one, Howard. All a dynamic background subtraction is doing is subtracting noise ions, i.e. those masses that were found via deconvolution algorithm or chromatogram deconvolution algorithm that did not have a peak shape to them. They become noise ions. They're constant throughout the entire TIC. When we do that dynamic background subtraction, all that we're doing is subtracting that out in the sample information window or the TIC window. That's all that's doing. When you think about it, what are we doing here in quantitative analysis? One of the first steps that the quant algorithm does is it does an extracted ion chromatogram from the left delta RT to the right delta RT of the target ion and the qualifiers. And that's all that you're seeing in there. That's all that it's doing. Well, if I'm doing an extracted ion chromatogram, for example, in Howard's window here right now of an MRM transition, 150.1 to 119.3, I don't have to worry about any noise in that particular chromatogram because that's all I'm looking at is the 150.1 ion and the 119.3 ion. That's all that I'm looking at. So taking that out is not really doing dynamic background subtraction, taking out any noise is not really influencing this extracted ion chromatogram. The nature of the extracted ion chromatogram is already getting rid of that noise. So we're not worried about that. All that we're doing with dynamic background subtraction is subtracting out the noise in the TIC. It has a lot of calculation or overhead time involved in there because if you turn dynamic background subtraction on, it has to run through this deconvolution algorithms, find out which ions are real ions and which ions are noise ions. So that's basically the answer there.